Ohm's law. When you first think about electricity, when you even first consider it really, you should be aware that there are really only three basic phenomena you need to know about. 1. Voltage, represented by V with a unit volts. 2. Current, represented by I with a unit amps. 3. Resistance, represented by R with a unit ohms. Voltage. Voltage is nothing more than potential. On its own, sitting still, it can do nothing. Each of us, when we're born, have the potential to change the world. But as long as we sit and watch TV and do virtually nothing, our potential is not realized. In terms of electricity, think of a 9-volt battery. It has the potential to supply 9 volts. It has 9 volts inside it. But sit it on your coffee table, alone, unconnected to anything, while you watch TV, its potential will not be realized, but it still contains 9 volts. Current. As we've said, voltage can do nothing on its own. It has to flow or move before it can accomplish anything. When water flows in a river, it creates a current. When voltage flows in a circuit, it creates a current. Imagine you are sitting at home and you suddenly want to bake a cake, but you have no ingredients. You have the potential to go to the market, buy ingredients, return home, then bake a cake. That potential is your voltage. The act of physically going to the market, buying ingredients, returning home, and baking the cake is your current. Once you put your potential in motion, you're actually doing something. Same with electricity. When a voltage is supplied and current flows, then the electricity is doing something. Resistance. Whenever something tries to do anything, it will encounter resistance. When a plane flies, it encounters wind resistance. When a car drives, wind resistance and friction of the road. From the last example, if you were going to put your potential to bake a cake to work, let your current flow by going to the market, buying ingredients, returning, and baking the cake, you too will encounter resistance. First, you will encounter gravity when you try to get out of your chair, wind resistance and road friction as you drive. There will probably be traffic on the road. There may be a long line at the market, all forms of resistance. These resistances all together will determine how difficult it is for you to get that cake baked. The less traffic and shorter lines means you don't have to work as hard to get it done. Your current can flow more freely. The less resistance you meet, the more current you can have. The more resistance you encounter, the less current you can have because it's more trouble for you to do your thing. Again, same with electricity. There is, in reality, resistance in everything electric current meets. It can be low resistance or it can be high, but it will be there. There is resistance in a given length of wire. There is resistance in every electrical component, resistors especially. Everything has resistance. I know there are components other than resistors. Everyone knows that. But even those components are resistors of sorts. Capacitors and inductors are really just frequency-dependent resistors. Even semiconductors like diodes and transistors are resistors which can be controlled by current and voltage, but you'll learn more about that as you go along. So how do these three things, voltage, current, and resistance, fit together? In 1827, Georg Ohm published his work regarding resistance in the physics of electricity. Even though Ohm's law is considered commonplace today, that wasn't so when his work was published. His findings were met with much resistance from German educational institutions. Ironic, considering the topic of his work, don't you think? His work eventually led to the unit for resistance, the ohm, being named in his honor. Ohm's law simply states, voltage equals current times resistance. Mathematically, V equals IR. This allows you to determine any one of these variables given the other two. Let's take a look at some examples.
Okay, don't worry, these won't be extensive examples, and
You'll have to excuse the image stabilization on the camera. It makes it jump a bit, but let's say we had a battery. That was horrible. This is the symbol for a battery. Let's say that battery was 10 volts. And in the circuit with it, we have a resistor, which is 10 ohms. Obviously, through this circuit, there will be some current I which flows. So with Ohm's law, V equals IR. To determine this current, we simply put in the voltage, keep the I, multiply that by the resistance. Fancy little algebra. "10 volts divided by 10 ohms equals 1 amp." That was example number 1. Fairly simple. Example 2. Number 2, if we have another battery and in the circuit with it, we have a resistor which is 100 ohms, and the current flowing in this circuit is 120 milliamps. How do we determine the voltage of the battery V? So, again, V equals IR. V will be equal to 0.120 amps. See, we changed this from milliamps to amps, so we shift the decimal 3 places. Times 100 ohms. V equals 12 volts. Times 100. Move the decimal place in 2 places. V equals 12 volts. Very simple. This is the simplest electrical law there is, but probably the best. Example 3. We have another battery. Keeping it simple here. Another battery. It's 9 volts. In the circuit we have a resistor of unknown value, and through this circuit there is 1 milliamp of current flowing through this resistor R. Again, not much to it. V equals IR, so 9 volts equals 0.001 amps times resistance R. Don't forget to change your units on your current here. That's very important, or you will receive the wrong answer. Use a little algebra to rearrange. R equals 9 volts divided by 0.001 amps, and that will give us 9,000 ohms, which equals 9 kilo ohms. That's really about all you need for examples.
Ohm's law is the most fundamental of all electrical laws. Regardless of how complex the circuit, once it's simplified, you will find that Ohm's law typically has the final say in the analysis of that circuit.